Tonight I want to correct something that almost everyone believes about the sky. You were taught, and you have never had cause to doubt it, that the sky is blue, that there is a blue thing above your roof the way the grass below it is green. It is a picture you have carried since you were small, and it happens to be wrong. There is no blue up there. If you rose 10 kilometers and filled a jar with the deepest part of it and carried the jar down to your bedside, you would be looking at an empty jar. That is where we will begin. After that, the clouds, which weigh as much as 100 elephants and float anyway. Then the stars, which are perfectly steady and only appear to tremble. And last, why the world sounds different at night. Before we begin, if you find these nights useful, subscribe. Only if you truly do. I would rather have a small room of people who want to be here than a large one that does not. And tell me in the comments where you are listening from tonight and what the hour is where you are. I am always curious who is out there in the dark and how far apart we all are. Now, lower the light in your room. If you have something that hums quietly, a fan, an old clock, let it run and stop looking at the screen. There is nothing on it worth your eyes. Settle into whatever position you intend to sleep in, the real one, not a polite one. Then close your eyes and I will begin. Let us begin by taking something away from you, gently, and giving it back before the chapter is over. There is no blue up there. I want to say the strange part first, plainly, in case you are asleep before the explanation arrives, which would be entirely fine. The air above your roof has no color in it, none at all. There is no blue dust in the sky. There is no blue ceiling, no blue lining, no blue gas, no blue anything. The sky is made entirely of colorless air, and the sky is blue. And both of those things are true at the same moment, and neither one is a trick. The space between those two facts is what I would like to fill for the next while, slowly, with the fire going down beside me. Start with the light rather than with the air, because the light is where the color actually lives. Sunlight looks white, or it looks like nothing at all, which as far as your eye is concerned is the same thing. But white is not a color so much as a crowd. Every color is in there, packed together, traveling as one, and they part company only when something makes them. In this study, in the afternoon, the sun comes in through the left window, and there is a heavy glass paperweight on the sill that I have never moved. Partly because I am not a tidy man, and partly because of what it does at about 4 o'clock. The light goes into the glass and comes out the other side no longer white. It lands on the floorboards as a small, soft band of red, orange, yellow, green, blue, and violet. Always in that order, always the same order, never once in my life in a different order, and it creeps very slowly across the wood as the afternoon goes on. That order is not a decoration, it is a ranking. The colors are lined up by size. Light travels as a wave, in the way that a swell travels across water, and every color is a wave of a different length. Red is the long one, a slow rolling wave with a great distance from crest to crest. Violet is the short one, quick and tight and closely spaced. All the others lie in between, in exactly the order on my floorboards, longest to shortest, which is why the band never rearranges itself. The lengths themselves are almost comically small. A red wave measures about 700 billionths of a meter from one crest to the next. A blue wave, something nearer 450 billionths. You do not need to keep those numbers. You need only the relation between them, which is that the blue wave is roughly half again as tight as the red one. And that small difference in tightness is about to be responsible for the entire color of the daytime sky, for every sunset you have ever stopped walking to look at, and for the fact that the sky outside your window is black tonight. Nothing else is required, just that one difference in size applied to an ocean of colorless air. Now the air, which is the other half of it. You are lying underneath a very great deal of air. The atmosphere holds a number of molecules that has no useful name, mostly nitrogen, a fifth of it oxygen, and a little of everything else. They are enormously far apart by the standards of a solid thing, and enormously crowded by the standards of empty space. They drift and collide and wander, and never once hold still. Every ordinary breath you take tonight will contain more molecules than there are grains of sand on all the beaches of this world. That is not a figure of speech, and I have never found a way to make it sound reasonable. You will do it several hundred times an hour, all night, without supervising any of it, without waking to check. And each of those molecules is minute compared with a wave of light. Not slightly smaller, about 1,000 times smaller than the wave that washes over it. So picture the encounter honestly, because this is the entire mechanism, and everything else in this chapter simply follows from it. A wave of light comes down out of the sun and meets a molecule of nitrogen standing in its path. The molecule is 1,000 times too small to block that wave, to stop it, to cast any shadow at all. What the molecule can do is be nudged. The wave washes over it and tugs its electrons back and forth a little, and the molecule, having been tugged, sends out a small wave of its own. Not forward, in no particular direction. Sideways and upward and backward and down, all at once. That is scattering, and it is the whole of it. The molecule is not blocking the light. It is catching a little of it and throwing it about at random, like a person in a crowd who catches a ball only in order to toss it somewhere else. And here is the one detail that makes the sky. A molecule is far better at doing this to short, tight waves than to long, lazy ones. A long red wave rolls over it as though it were not there, barely disturbed, and carries on straight down to the ground. A short blue wave gets caught and flung aside far more readily. At the blue end of the crowd, the scattering happens something like 5 or 6 times as often as at the red end, and at the violet edge closer to 10. So the sunlight coming down through the air is being sorted, quietly, without anyone arranging it, without any machinery, simply as a consequence of size meeting size. The reds and oranges and yellows mostly go straight through and arrive in a direct line from the sun. The blues get intercepted, thrown sideways, intercepted again by another molecule, thrown again, and again, and again, until they are bouncing about the whole ocean of air like a rumor in a small town. Which means that by the time the blue light reaches your eye, it is not coming from the sun anymore. It is coming from everywhere. You look up at a patch of sky far away from the sun, a patch with nothing whatever in it, and light arrives at you from that empty patch, and it is blue, because blue is the color that got thrown around until it lost its direction. The sky is not lit. The sky is what light looks like after it has been knocked off course. That is the sentence I would keep if you were to keep only one. Every blue you have seen overhead, on every clear day of your entire life, was sunlight that never managed to reach the ground in a straight line. There is a small honesty I owe you here, because you may have noticed a gap in what I have said. If short waves scatter most, and violet is shorter than blue, then the sky ought to be violet. It is not. It never has been anywhere on this planet in all of its history. The reason is a quiet conspiracy between the sun and your own eyes. The sun does not put out its colors in equal measure. There is simply less violet in sunlight than there is blue, from the beginning, before any air is involved. And your eyes, which are not instruments but old and specialized animals in their own right, are not very interested in violet. You carry 3 kinds of color sensor at the back of each eye, and the shortest of the 3 responds to blue far more eagerly than it responds to violet. So the violet is up there. It is mixed into the sky, scattered even harder than the blue, arriving at you from every direction along with everything else. And your eye considers it and shrugs and reports blue. The sky as seen by a different creature with different sensors would be a different color. Not a different sky, a different reader. At night I find that a comforting thought rather than an unsettling one. The blue was never a property of the thing above you. It was always a meeting. A particular arrangement of light and air and the equipment behind your eyes. 3 things agreeing on a color, the way 3 people in a room agree on the temperature. And once you know that the blue is scattered light rather than a painted ceiling, the sky becomes readable. It begins to tell you things. Chiefly, it tells you how much air the light came through to reach you, and you can learn to see that as easily as you see the weather. On a high mountain, the sky is deeper and darker than at sea level, almost inky directly overhead. I saw that many times as a young man in Switzerland, and did not know then that I was looking at a shortage. Up there, standing above a fair portion of the atmosphere, there is less air overhead to do the scattering. Less blue is thrown down at you. And the darkness of space begins to show through the thinning, the way a wall shows through thin paint. From the window of an aircraft, the same effect goes further. At cruising height, the sky above the wing is a very dark blue, dark as a late evening at noon, and the reverse holds just as reliably. Look at the sky low down near the horizon, and it is always paler than the sky at the top. Not because anything different is happening there, but because you are looking along a much longer path through the air. The light has been scattered so many times over that distance that the colors have mixed back together, and mixed light is white light returning. Over a hot horizon, in heavy humid air near the sea, the whole sky goes pale and washed out. Now there is something else in the way. Water droplets and dust and haze, which are not 1,000 times smaller than a wave of light, but roughly the same size as one, and particles of that size do not sort the colors at all. They scatter everything equally. Everything scattered equally is white. A white sky is not a different mechanism. It is the sorting switched off, by particles too large to be fussy. There is a version of this you can see without looking up at all, and I think it is the loveliest of them, because it happens at eye level, and people have been painting it for 500 years without always knowing what it was. Look at a range of hills in the distance on a clear day. The near ones are green or brown or whatever they happen to be. The ones behind them are paler and slightly blue. The ones behind those are bluer still and softer at the edge. And the farthest ridge of all, at the limit of what you can see, is a pale ghost of blue, barely distinguishable from the sky above it, with no detail left in it whatever. Nothing is on those hills. There is no blue haze hanging over the far ones, and not the near ones. What lies between you and the far ridge is simply more air, 20 or 30 or 50 kilometers of it, doing horizontally exactly what the sky does vertically. Blue light from the sky above that air is being scattered sideways into your eye all along the way, laid over the hill like a thin veil, and the farther the hill, the more veil there is. Leonardo wrote this down, in Italy, long before anyone knew what light was made of. He told painters to put distant things in blue and to soften them, because that is what the eye reports, and painters have obeyed him ever since without needing the physics. So when you look across a wide valley in the evening and feel that particular sense of distance, that is not a mood. You are seeing air. You are seeing directly how much world is standing between you and that ridge, translated into a color. I always like that the sky sits between us and everything far away, so quietly that we mistake it for emptiness. And now let us do the evening, which is the same physics lying down. At noon the sun is more or less above you, and its light comes down the short way, through perhaps 8 or 10 kilometers of thick air, and then a long, thin tail of almost nothing at all. That is a brief passage. Most of the red and yellow arrives untouched. A portion of the blue is scattered across the dome overhead, and the day looks the way days look. At sunset, the sun stands at the edge of the world. Now its light does not come down to you. It comes in, at a long slant, sideways through the entire thickness of the atmosphere, skimming along the curve of the planet for hundreds of kilometers. The distance that light travels through air is something like 30 or 40 times greater than it was at midday. 30 or 40 times as many chances to be scattered. Over that long, slanting crossing, the blue does not stand a chance. It is caught and flung aside early, spread out into the sky above other places, scattered away and away until there is essentially none of it left in the beam that reaches you. Then the green goes the same way. Then the yellow begins to thin. What survives the crossing and arrives at your eye is the long, slow red that hardly notices molecules at all. So the red of the evening is not something added at the end of the day. It is what is left. It is a subtraction. Sunset is the color of ordinary sunlight with the blue taken out of it by a great deal of air, and the blue that was taken out is not lost anywhere. It is simply overhead somewhere else, being noon for somebody. That has always struck me as the most companionable fact in the whole business. When the light in your window turns orange, the blue that used to be in it is being handed westward, to people who are not thinking about you at all, and who will hand their own blue on in a few hours to someone farther on again. It goes around and around the turning world all day, every day, this passing along of the blue, and it has never once stopped, and no one has ever had to organize it. Then the sun goes under the edge, and there is the half hour that follows, which is my favorite light of the day, and I suspect most people's, whether or not they have ever said so. The whole sky becomes an even deep blue, filling the air from horizon to horizon, the color of good ink diluted in water. There is no glare in it and no direction to it. It comes from everywhere at once. That is light which is no longer reaching you directly at all. The sun is beneath the horizon. It is lighting the air above you from underneath, and only the scattered part of it is coming down. Every bit of light in your street at that hour has been thrown sideways at least once to get to you. You are seeing the leftovers of a day that has already ended somewhere else, which seems to me a very reasonable thing to be looking at while you are getting ready for bed. How long that lasts depends on where you are standing. Near the equator, the sun goes down steeply, straight through the horizon, and the blue half hour is short and the night arrives briskly. Farther north, the sun goes down at a slant, sliding along under the edge rather than dropping through it, and the twilight stretches out. In the far north in summer, it never finishes at all. The sun stays just below the rim all night, and the sky never gets past that deep blue, and people up there sleep with the curtains drawn against a light that has no sun in it. At the poles, it is stranger still. When the sun finally sets in autumn, it does not become night. It becomes twilight, and the twilight lasts for weeks, a slow gray-blue nothing, neither day nor dark, before the true night settles in for the winter. And then, tonight, black. Here is what is worth noticing about the darkness outside your window at this moment. The air has not changed. Every molecule that was making the sky blue this afternoon is still up there, still drifting, still colliding, still perfectly capable of scattering light in all directions. Nothing has been taken away. The apparatus is intact and idle. The sky is black tonight because there is no sunlight passing through it to be scattered. That is the whole explanation. The blackness is not a substance either, any more than the blue was. It is the same air off duty. I like to think of it in that way at night. The sky is not doing anything difficult overhead. It is holding still, unlit, waiting to be given light again in a few hours, at which point it will do exactly what it did yesterday, without being told, without being maintained, without anyone having remembered to arrange it. You can see the proof of this on the moon, where men have now stood. The moon has no air worth the name, and so the moon has no blue sky, no white sky, no sunset and no twilight. It has a black sky at midday. The sun stands up there in full blaze, and around it, in every direction, the sky is as black as it is at midnight, and the stars are up there in it the whole time. The shadows on the ground have edges like knife cuts, because there is no air to soften them and no scattered light to fall into them. A shadow there is not dim. It is simply darkness with a hard border, sitting next to blinding light. That is what a world looks like with the scattering switched off. Harsh light, black sky, hard shadow, no glow, no dawn. The sun comes up over the lunar horizon like a lamp being turned on, with no warning color before it and nothing softening the moment. Everything gentle about our own light is the air doing it. The blue overhead, the golden hour, the glow that lingers after the sun has gone, the fact that a shaded corner of your bedroom is dimly lit rather than pitch dark, the reason you can see anything at all in the shadow of a tree. All of that is scattered light, which is to say light that was thrown off course by molecules and came at you from the side. The atmosphere is not only what you breathe, it is what makes the daylight kind. And it is thin. That is the part people rarely feel in their bodies. If you shrank this planet to the size of an apple, the whole of the breathable atmosphere would be about as thick in proportion as the skin on the apple. Half of all the air on Earth lies below 5.5 kilometers, which is to say below the summits of the larger mountains. You could drive to the edge of it in under an hour if the road went straight up. That thin skin of colorless gas is the entire reason the day is blue, the evening is red, and the light in every room you have ever sat in was soft. I should tell you, before I leave this, that I came to the subject myself late and by an odd road. It was in Zurich around 1910. I had not set out to explain the sky at all. I had become interested in a strange thing that happens to certain fluids when they are brought close to a particular temperature and pressure. They go cloudy, milky, opaque, glowing faintly for no visible reason, having been perfectly clear a moment before. Then you change the conditions slightly, and the cloudiness goes away again. It is called critical opalescence, and it was a small puzzle, which is the kind I liked best. The answer turned out to be that the fluid, which looks smooth, is not smooth. Its molecules are always drifting into small crowds and small emptinesses, thickening here, thinning there, a constant fine unevenness, never the same twice, never anywhere still. Ordinarily, those crowds are far too small to matter to light, but near that critical point they grow, and when they reach about the size of a wave of light, they scatter it powerfully, and the fluid goes milky before your eyes. And when I had the mathematics of that in my hands, I saw that the same reasoning, applied to ordinary air, gives the blue of the sky. Not qualitatively, it gives the shade of it, and the way it depends on the size of the wave, and the numbers came out right, so I wrote it down and published it. It is one of the papers of mine that almost nobody mentions, and it is one that I have always liked best of the quiet ones, because of what it says about the reason for the color. The sky is blue because air is never evenly spread. That is the true form of it. If the atmosphere were a perfectly smooth substance, uniform, every molecule at precisely the same distance from its neighbors, then all those little scattered wavelets would meet each other and cancel out in every direction except straight ahead. The sky would be clear and dark. The sun would hang alone in blackness at noon over a world with air in it. It is the imperfection that makes the color. The little crowdings and thinnings, the restlessness of a gas that will never sit still and has never once sat still in the history of this planet, that is what is blue. The great soft blue that has been over your head on every clear day of your life is the visible result of the air being permanently untidy. Tonight, there are 100 kilometers of that quiet air stacked above your roof. It is doing nothing at all. It is not being held up. It is not being maintained. It weighs on nothing and asks nothing, and it has no color in it whatever. And in a few hours, without any help and without any announcement, it will start sorting sunlight again. The blue will come back over your house, whether or not you are there to receive it. It will most likely arrive while you are still asleep. It will not need you to have understood any of this, and it will not mind in the least that you did not stay awake for the end. Next, the clouds, which weigh as much as a herd of elephants and float regardless. But there is no hurry to get there, and there never was. Let me give you the number first, because the number is the whole reason this chapter exists, and if you sleep through everything after it, you will still have had the best part. Think of an ordinary cloud, not a storm, one of those white heaped clouds that stand about on a summer afternoon, the kind a child draws, with a flat bottom and a piled top, drifting over a field with its shadow going along underneath it. That cloud weighs about 500 tons. 500 tons of water in the air over the field at that moment. It is roughly 100 elephants. It is more than a fully loaded aircraft, considerably more, and there may be 40 of these clouds in the sky above you on a pleasant day, and none of them is doing anything remarkable, and not one person in the field looks up with any concern. And that is only the small ones. A tall thundercloud, the kind that stands up in the late afternoon like a white mountain with a flat spreading top, holds some hundreds of thousands of tons. There are days in summer when the weight of water standing over a single country, quite still, quite silent, exceeds anything that has ever been built. So the question is not really a schoolroom question. It is a fair question, and I would like to answer it slowly. Why does it not come down? The first thing to understand is that you have been misled by your own eyes, and gently and for a good reason. A cloud looks like an object. It has an edge. It has a shape you could draw. It moves as one thing. It casts a single shadow, and children point at them and say that one looks like a horse, and it does look like a horse, and it will still look faintly like a horse 10 minutes later. But there is no object there. There is nothing in the sky with a boundary. What you are looking at is not a thing at all, and once you see that clearly, the weight stops being a puzzle and becomes something else, something I think is more restful. Let me take it apart properly. That 500 tons of water is not gathered anywhere. It is not a lake up there. It is not held in a bag. It is not resting on anything. And it is not in any sense together. It is divided into droplets, and the droplets are extraordinarily small. A cloud droplet measures about 20 thousandths of a millimeter across. You cannot see one. You could not see 100 of them side by side. They are far smaller than the finest mist from a garden hose, far smaller than anything you would call a drop, so small that if one landed on your hand you would never learn of it. And the cloud contains in every cubic meter of itself about 100 million of them. That is the number that dissolves the puzzle. So let me say it again more slowly. Take a box of cloud 1 meter along each edge, the size of a small table. Inside that box there are 100 million separate droplets of water, and the total amount of water in the box, if you gathered every one of them together, would be about half a gram. Half a gram. Less than a teaspoon, spread through a volume the size of a table. The 500 tons is real, but it is spread across a kilometer of sky in every direction, and at any point inside that cloud there is almost nothing there. Consider how far apart those droplets are standing. 100 million of them in a cubic meter sounds crowded, and it is not. Work out the spacing, and each droplet sits about 2 millimeters from its nearest neighbor. For something 20 thousandths of a millimeter across, that is a distance of about 100 times its own width. Scale it up to something you can stand in. If a cloud droplet were the size of a person, the next droplet would be standing 50 meters away, and the next one 50 meters beyond that, in every direction, out to the horizon. Not a crowd, a very sparse population, spread over an enormous country, out of shouting distance of one another. So when you fly into a cloud and the window goes white and the wing disappears, you have entered something that is almost entirely air. The white is not thickness. It is only the sheer number of surfaces the light is bouncing off between you and the wing. If you could take a cloud a kilometer across and gather all of its water into one place, you would get a pool a few meters wide. That is the whole of it. Everything else you are looking at, the piled shoulders, the bright top, the deep shaded underside, all the architecture of the thing is air and light, an empty distance between droplets. This is why the weight never presses on anything. There is no 500 tons anywhere. There is half a gram here, half a gram there, half a gram a table's length away, repeated across a piece of sky the size of a town. But I have not yet answered the question, only softened it. Half a gram is still half a gram. Water is still heavier than air. A droplet, however small, still weighs something, and gravity has no minimum. Gravity does not overlook small things or grant them exceptions. It pulls on each of those 100 million droplets exactly as it pulls on you in your bed. So why do they not fall? Here is the honest answer, and it took me by surprise the first time I properly followed it through. They do fall, all of them, continuously. Every droplet in every cloud in the sky tonight is falling at this moment, and has been falling since it formed, and will fall until it is gone. Nothing up there is suspended, nothing is held, nothing is exempt. The entire sky is coming down. It is simply coming down very slowly. A cloud droplet falls at about 1 centimeter per second. Let that sit for a moment. 1 centimeter each second. A meter and a half in a minute. It would take that droplet the better part of a day to fall from the cloud to the field below, and a whole night to fall the height of a mountain. Compare that with a raindrop, which is 100 times wider and falls at 7 or 8 meters per second, fast enough to sting your face and to be heard on a roof. The cloud droplet is doing the same thing as the raindrop. It is falling. It is falling 600 times more slowly. The reason is one of the most reliable rules in nature, and it explains far more than clouds, so it is worth taking gently. When something falls through air, two things are set against each other. Gravity pulls, according to how much stuff there is. Air resists, according to how much surface is pushing through it. Now make the object smaller, and those two do not shrink at the same rate. Half the width of a droplet, and its weight drops to an eighth, because weight follows volume. But its surface drops only to a quarter. So the smaller thing has, in proportion to its weight, more surface to be slowed by. Make it smaller again, and the disparity grows again. Keep going, down to 20 thousandths of a millimeter, and you arrive at an object which is almost all surface and hardly any weight, wading through air that behaves toward it not like a thin gas but like syrup. You have watched this happen many times without giving it a name. Drop a stone and it falls hard. Drop a feather and it wanders. Shake out a blanket in a shaft of afternoon light, and the dust comes off it in a slow cloud that seems to be hanging in the air, drifting sideways, going nowhere, and that dust is falling too, at about the same crawl as a cloud droplet, and it will take 20 minutes to reach the floor, and you will have stopped watching long before it arrives. There is a beam of light across this room in the afternoon, from the left window, and the dust in it turns very slowly, and I have sat and watched it far longer than a serious man should. That is the sky, in miniature, on a rug in Princeton. Smallness changes what falling means. Below a certain size, falling stops being an event and becomes a way of being present. The droplet is not defying gravity. It has simply been reduced to the point where gravity is no longer the fastest thing acting on it. And now the last piece, which is the one that turns a slow fall into no fall at all. The air is not still. Air rises. Not everywhere and not always, but constantly and in great quantity, and particularly under a cloud. The ground warms in the sun, unevenly, a plowed field faster than a wood, a road faster than a lake, and the air over the warm places grows lighter and begins to go up in slow columns. These are the thermals, and they are why the hawk circles without beating its wings, and why gliders can stay up all afternoon without an engine, and why the buzzards go round and round over a hillside in the middle of the day. A gentle thermal rises at a meter or two per second, a weak one, a tired one, at a few centimeters per second, and a few centimeters per second is all it takes. The droplet is coming down at 1 centimeter a second through the air. The air is going up at 10. The droplet is therefore rising at 9 centimeters a second while falling the whole time, exactly as a person walking down a moving staircase that is going up will nonetheless arrive at the top. That is the answer, and I want to say it in the way that I find most restful. The cloud is not being held up. Nothing is holding it. There is no support anywhere in the sky, no surface, no shelf, no exception granted. Every part of it is falling and always has been. It is simply falling through something that is going up faster, and so it stays. I find that a better thought at night than the idea of the cloud being held. Being held requires a holder, and a holder can tire and can let go. Nothing up there is being held, and nothing up there can be dropped. It is all going down gently, at the speed of dust in a sunbeam, into air that is going up, and the two rates have been in this loose agreement over your part of the world for as long as there has been a world. Nothing is working. That is the point I keep circling back to on these nights by the fire. There is no effort up there, not a joule of it. The cloud does not strain, the air does not push, the water does not resist. Everything is doing the easiest available thing at every moment, and the result is 500 tons standing over a field in perfect silence all afternoon. But I have described the cloud as though it were a fixed population of droplets, going up and coming down, and it is not. This is the part that took me longest to properly believe, and it is stranger than the wait. The cloud you look at is not the same cloud from one minute to the next. Not merely changed, replaced. At the bottom of a cumulus cloud, air is arriving all the time from below, moist and warm, and it cools as it rises, and its water condenses out into new droplets. Cloud is being manufactured continuously along the entire underside. At the top and around the edges, where the cloud meets drier air, the droplets are evaporating. They shrink and vanish, and the water goes back to being invisible vapor, and the edge retreats. So a cloud is a place where two processes meet: water becoming visible at the bottom, water becoming invisible at the sides and top, and the boundary between them holding still while the material streams through it. A summer cumulus can replace its entire contents in something like 10 or 20 minutes. Not one droplet that was in it when you first looked is in it now, and yet it still looks like a horse. I want to give you the right image for this, because there is a very good one. It is a flame. The flame on this log has a shape. It has a definite edge, a color, a form you could draw, and if you sat with it for a while, you would say it is the same flame it was 5 minutes ago. But nothing in that flame stays. Gas rises into it and burns and leaves as heat and smoke, continuously. And what persists is not any material at all. What persists is the shape of a process, standing still in a stream of stuff going through. The cloud is a flame made of water, burning very slowly, upside down, in the cold. Or think of a standing wave in a river, the smooth curl of water over a submerged stone. The wave stays where it is all day. You could come back next year and find it in the same place. But no water stays in it for more than an instant. The river pours through it endlessly, and the shape does not move. There are a great many things in this world that are shapes rather than substances. A waterfall, a whirlpool, a dune, which is sand walking slowly downwind while the hill appears to stand still. A city, come to that. And you, if we are being exact about it. Almost every atom in your body will be exchanged over the coming years, replaced from the food and water and air passing through you, and you will remain, recognizably, yourself, a pattern holding its shape while the material streams through it. You have already done this several times over. You did not notice, and nothing was lost. The cloud does it in 20 minutes, which is only the same trick performed impatiently. Now let me show you something you have looked at 10,000 times and probably never questioned, because it is the finest visible evidence of everything I have just said. Go out on a summer day with those heaped clouds standing about, and look along the sky rather than up at it. The bottoms are all at the same height, every one of them. Across the whole landscape out to the horizon, the flat undersides of every cloud lie in one perfect plane, as though they were all resting on a sheet of glass that has been laid across the sky. The tops are various. Some are piled high, some are low and modest, some are ragged, and some are smooth. But the bases line up with the precision of a ruled line, and they do it over hills and valleys alike, and over towns and lakes, without exception. Nobody arranged that. There is nothing there. So what makes the line? It is a temperature made visible. Air cools as it rises. It has to, and the reason is simply that it expands into the thinner air above, and expansion cools a gas. The rate is dependable, about 10 degrees for every kilometer of climb, in dry air. An air can hold a certain amount of water as invisible vapor, but only a certain amount, and the amount depends sharply on temperature. Warm air can hold a great deal. Cool air can hold less. Cool it far enough, and it can no longer hold what it has, and the water must come out of hiding and condense into droplets. So a parcel of moist air leaves the warm ground, rises, cools as it goes, and at some particular height it reaches the temperature at which it can no longer keep its water invisible. At that instant, cloud appears. And since the air across a whole region shares roughly the same temperature and the same moisture at ground level, every rising parcel for 100 kilometers around reaches that point at the same altitude. That flat sheet is the height at which the sky becomes cold enough to give up what it is carrying. It is not a surface. Nothing is resting on it. It is a line drawn in the air by arithmetic, and you can see it from your garden. On a humid day the line is low, because the air is already nearly full and does not have to climb far to be overwhelmed. On a dry day it is high, and the clouds stand far up with a great empty space beneath them. Pilots know the height before they take off. Anyone can learn to read it. I have always liked that particular fact. Somewhere over your house tonight, there is an altitude at which the air would have to give up its water, and it is a real and calculable height, and nothing marks it, and no cloud happens to be there at present to show you where it is. There is one more thing inside every droplet that I have not mentioned, and it is my favorite fact in this chapter, and I have saved it deliberately. Clean air cannot make a cloud. You would think that cooling moist air far enough would be sufficient, and in the world it is, but in a laboratory it is not. Take truly pure air, with nothing whatever floating in it, cool it past the point where it should condense, and nothing happens. Cool it further and still nothing happens. You can cool it to several times over what it should be able to hold, and it will stubbornly stay clear. Water will not condense out of the air onto nothing. It needs a surface to begin on. A few molecules of water coming together on their own make a droplet so tiny and so sharply curved that it evaporates again almost immediately, and so the cloud never gets started. What it needs is a speck. Something already there, however small, for the water to gather onto. And so every one of those 100 million droplets in every cubic meter of every cloud has at the center of it a solid particle of something. Now consider what that particle is likely to be. Very often it is sea salt. Waves break all over the world, all the time, and the bubbles in the foam burst, and each bursting bubble flings a few unimaginably small crystals of salt up into the air, and they rise and they travel. A great deal of the rain that falls on the middle of a continent formed on salt that came out of an ocean. Often it is desert dust. The Sahara sends a plume of fine dust across the Atlantic more or less permanently, and some of it falls into the Amazon, where it fertilizes the forest, and some of it goes up into cloud and comes down in rain over Europe. There are days in southern Europe when cars are found in the morning covered in a faint red film, and it is the desert, arriving by air, having ridden inside raindrops. And often it is life. Pollen from grasses, spores from fungi, fragments of leaves and bacteria, which are very good at this and appear to encourage ice to form around them, and which are lifted off forests in enormous numbers and carried up. Also smoke from fires, and ash from volcanoes, and dust from your own road. So there is nothing in the sky that is made only of sky. Every drop of rain that has ever fallen on your face was assembled around a fragment of the world. A grain of salt from a wave that broke off some coast, or a mote of a desert you will never visit, or a piece of a forest. The clouds are built out of the ground. They are the world, lifted up, wrapped in water, and returned. While we are here, let me settle the color, since we spent the earlier part of the evening on the color of the sky, and this is the same question with a different answer. Clouds are white for the reason that the sky is not. The molecules of air are 1,000 times smaller than a wave of light, and so they are fussy. They fling the short blue waves about and let the long red ones pass, and the sorting of those two is the blue overhead. A cloud droplet is not 1,000 times smaller than a wave of light. It is roughly 30 times larger, and a particle of that size has no preference whatever. It scatters every color with equal enthusiasm, red as readily as blue, and sends them all back out mixed together. All colors together is white. That is the whole of it. Clouds are white because their droplets are too big to be selective, which is also why fresh snow is white, and sea foam, and crushed glass, and a bag of salt, and the head on a glass of beer. In every case, a clear, colorless substance has been broken into pieces large enough to scatter light without sorting it, and the result is always the same brightness. Nothing has been added. Snow is only ice, which is clear, arranged so as to reflect confusion. And then the dark underside of the thunderclouds, which people take for a different substance, some heavier and blacker water, gathering with intent. It is not. It is the same white droplets. There are simply so many of them through so many kilometers of depth that the sunlight falling on the top of the cloud is scattered again and again on its way down, and very little of it ever emerges at the bottom. The base is dark for the same reason a deep forest is dark at noon. Not because darkness has arrived, but because the light has been used up overhead. The top of that same cloud, seen from an aircraft at the same moment, is a blinding white mountain in full sun. So the clouds then, 500 tons over the field, and no lake up there, and nothing anywhere with an edge. 100 million droplets in every cubic meter, standing 50 of their own widths apart, each one falling at the speed of dust in a sunbeam, each one built around a grain of salt from some ocean or a moat of some desert. Air rising underneath them a little faster than they descend, so that everything falls forever, and nothing ever arrives. And the cloud itself not a thing at all, but a shape standing in a stream, remaking its entire substance every quarter of an hour, holding the outline of a horse throughout. There are clouds over you now. You cannot see them, and possibly there are none tonight, and the sky above your roof is clear. But somewhere within 100 kilometers there are certainly some, drifting in the dark, white where the moon reaches them, and invisible everywhere else. They do not stop at night. That is the thing I would leave you with. There is no shift change up there, no hour at which the thermals are told to keep going, nothing that needs to be maintained until morning. The droplets that are falling above your house at this moment will still be falling at 3 o'clock, and at 5, and will not have arrived. The bases will still be lying in their flat line at the height where the air runs out of patience with what it is carrying. And in the morning, whether or not anyone goes out to look, there will be new clouds standing over the fields, made of different water than tonight's, holding the same shapes. Let the sky carry its 500 tons. It has never once put them down, and it has never once been tired. Next, the stars, and why they tremble while the planets hold perfectly still. If you have a window near your bed and the night is clear, you may look out for a moment before we start. Or you may not. This works just as well from memory, and it will still be true in the morning. Find a bright star, low down, above the roofs. It is trembling. It shivers. It changes brightness. It seems to flicker as though the flame of it were being disturbed by something. And if it is low enough and bright enough, it will flash faintly with color, red and then green and then white again, several times a second. Now find a planet if one is up. Jupiter or Venus in the early evening, or Mars when it is out. You will know it because it is bright and because it is not doing any of that. It sits there. It shines with a flat, steady, untroubled light, like a lamp in a distant window, and it does not shiver at all. They look the same, two bright points in the dark, and one of them cannot hold still, and the other one will not move. That difference has been noticed by everybody who has ever looked, in every country, in every century. It is how the ancients told the wanderers from the fixed stars before they had any instrument to help them. And the explanation is not in the stars, and not in the planets either. Nothing out there is doing anything. The trembling is happening in the last few kilometers above your roof. That is what I would like to spend the next while on, where the shivering actually is, and why one kind of light picks it up and the other kind does not. Let me start with the light itself and how far it has come, because the scale of it makes the rest of the chapter behave properly. The star you are looking at is unimaginably far away. Not far in the sense that a city is far. The nearest star to us after the Sun is something like 40,000 billion kilometers off, which is a number that does nothing for anybody, so let us use the light instead, since the light is what we are discussing. Light is quick. It crosses this room before you could begin to notice. It comes from the moon in a little over a second, and from the sun in about 8 minutes. So the sunlight falling on your garden this afternoon left the sun while you were doing something else and had already forgotten about it. But from the nearest star it takes 4 years, and that is the nearest. The bright ones you can pick out easily from a bedroom window are much further. The light from Sirius, the brightest star in the whole night sky, has been traveling for a little under 9 years. The light from Rigel, in the shoulder of the winter sky, has been on its way for something like 800 years, which is to say that it left before anyone alive had a grandparent who could have been told about it. So consider what that light has been through, and then consider what it has not been through. It crossed 800 years of open space. Nothing happened. That is the remarkable part. Space between the stars is emptier than any vacuum ever produced on this planet, a few atoms in a volume the size of this room, and light passing through it is essentially undisturbed for century after century. It does not slow, it does not scatter, it does not fade in the ordinary sense, it does not get tired. It simply travels at the same speed, in the same direction, for 800 years, through the dark, while everything you have ever heard of happens on a small planet somewhere ahead of it. And then, at the very end of the journey, in the last 100 kilometers, having been perfectly steady for 8 centuries, it meets our atmosphere, and it starts to stumble. The whole of the trembling you are watching happens in the final 30 millionths of a second of a journey of 800 years. Everything that ever disturbed that light happened over your own house, more or less, and in a space you could drive across in an hour if the road went up. I have always found that a very good thing to know at night. Whatever is unsteady in the view is close by, and it is thin, and it is ours. Now, why does the air disturb it at all? We spend the first part of tonight on this without naming it. The air is not evenly spread. It never has been, and it cannot be. It is a gas, it is restless, it is warmed unevenly from below and cooled unevenly from above, and it is always full of parcels that are slightly warmer than their neighbors and slightly cooler than their neighbors, mixing endlessly, folding over on themselves, never once achieving uniformity anywhere. And warm air is slightly thinner than cool air, which means light travels through it very slightly faster, which means every one of those parcels bends light a little. That is the whole mechanism, and it is the same one that makes a spoon look broken in a glass of water, and the same one that makes the road ahead of a car shimmer on a hot day, and the same one that makes the view over a bonfire wobble. Light passing between materials of different density gets bent. A parcel of warm air sitting in cooler air is a lens, a very weak one with soft edges, but a lens. So the atmosphere over your house tonight is not a clear window. It is a thick stack of thousands of soft, shifting, invisible lenses, of every size from a hand's width to 100 meters, all drifting past one another at different speeds and different heights, forming and dissolving continuously, all night, over every square meter of the world. The starlight has to come down through all of it. And now something happens which I think is the best fact in this chapter, and hardly anyone knows it, and you can almost see it for yourself. Those weak lenses focus the starlight. Badly and briefly, but they do focus it. A parcel of air that happens to be shaped so as to converge the light will gather a little extra of it and concentrate it somewhere below. A parcel shaped the other way will spread it out and leave a thin patch. So the starlight arriving at the ground is not spread evenly across your garden. It lands as a pattern. There are patches on your lawn tonight, from each individual star, where that star's light is a little brighter, and patches where it is a little dimmer, and they are perhaps a hand's breadth across, or a little more. A shifting, mottled pattern of light and shade, cast by a single star, lying over the grass and the roofs and the parked cars, far too faint for your eyes to see as a pattern, and it is moving. It streams across the ground, because the air that made it is moving, high up, in the wind at the top of the sky. Those winds are strong. At 8 or 10 kilometers, where the jet stream runs, air moves at 100 or 200 kilometers an hour, permanently, over most of the world. So the pattern sweeps past you at something like that speed. Your eye is a small hole. The pupil, at night, opens to perhaps 7 millimeters. That is a very small window through which to sample a pattern that is mottled on the scale of a hand. So your eye sits in one patch, and then a fraction of a second later, it is in another, and then another. Bright, dim, bright, bright, dim. Tens of times each second. That is the twinkling. That is all it has ever been. The star is not changing. The pattern of its light on the ground is racing past your face, and your pupil is too small to average it out, and so you receive a flicker. When you watch a star tremble, you are watching the wind at the top of the sky, translated into light and delivered to your window. Faster winds aloft, faster twinkling. It is a wind gauge that anybody can read and nobody was ever taught to. And I should say, since it follows immediately, that your two eyes are seeing slightly different patterns, being about 6 centimeters apart, and so a star is twinkling slightly differently into each of them. And a person standing in the next street is getting a different flicker again from the same star at the same instant. There is no such thing as the twinkling. Every observer has their own. Which brings us to the planets, and to why they refuse. Everything I have described depends on one thing that I have not yet said aloud. It depends on the star being a point. A star, however enormous it actually is so far away that it arrives here as a single point of light, with no width whatsoever. No instrument on this planet in ordinary conditions can show you a star as a disk. Even in the great telescopes, a star is a point, and the small round blob you see in a photograph is not the star. It is the blur that our own instruments and our own air impose upon a point. So all the light from that star comes down through the atmosphere along essentially one path, one route, one stack of lenses. And whatever those lenses do to it, they do to all of it at once. Brighten it all, dim it all, shift it all. There is nothing to average against. A planet is a different thing entirely. Jupiter is not far away in the sense that a star is far away. It is in our own household, and it is large. When you look at Jupiter, it presents a small disk to you, perhaps 1/40th of the width of the full moon. That is too small for your eye to resolve, which is why it still looks like a point to you. Your eye cannot separate detail finer than about 1/60th of a degree, and Jupiter's disk is finer than that, so you see a dot. But the atmosphere is far more discriminating than your eye, and to the atmosphere, that disk is not a point. It is a broad object made of an enormous number of separate points, side by side, and the light from each of those points comes down through the air along its own slightly different path, through its own stack of lenses, and lands as its own separate mottled pattern. So the pattern arriving at your eye from Jupiter is not one pattern. It is thousands of them, laid on top of each other, each one flickering, all of them out of step. And when you add together thousands of independent flickers, they cancel. Where one is bright, another is dim. The sum is steady. It is the same reason that a crowd of 1,000 people produces a smooth sound, while 3 people produce a lumpy one. That is the whole difference between the two lights in your window. Not distance, not brightness, not what they are made of. Width. The star is a point, and its flicker has nothing to argue with. The planet is a small disk, and its flickers argue each other into silence. Once you know that, the night sky becomes readable in a way it was not before, and you can check every part of what I have said from a garden without any equipment. Look at a star directly overhead. It twinkles a little, and calmly. Look at a star just above the roofline. It twinkles violently. That is the same fact from the earlier part of tonight, wearing a different coat. Straight up, the starlight passes through the shortest possible column of air. Near the horizon, it comes in at a long slant and travels through many times as much of it, and therefore through many times as many of those soft, shifting lenses, and it arrives thoroughly disturbed. The horizon is where the sky is most agitated. It always has been, and that is where you will see the colors, which are worth waiting for. Find Sirius on a winter evening when it is still low in the south, and watch it for half a minute without looking away. It flashes. Red, then a hard clean green, then white, then blue, faster than you can name them. Those flashes are the same effect with one addition. When air bends light, it bends the colors by slightly different amounts, exactly as the paperweight on my windowsill does. So the mottled pattern that a star throws across your garden is not a single pattern after all. There is a red one and a green one and a blue one, lying almost on top of each other, but not quite, and displaced from one another by a little. So as they sweep past your eye, you catch first a bright patch of one color, and then a bright patch of another. The star has not changed color. Your pupil is being handed the colors separately. People report this to astronomers regularly, having seen a low bright star flashing in several colors and moving oddly, and being certain that they have seen something extraordinary. They have. They have seen the entire atmosphere at work in a single point of light. And here is the small irony that professional astronomers live with. The nights that look most beautiful to you, the crisp ones after cold weather has come through, when the air seems scrubbed and every star is hard and sparkling, and the sky looks like the inside of a jewel, those are the worst nights of all for a telescope. All that sparkle is turbulence. The air is clear, but it is churning. The best nights for a telescope look flat and slightly dull. The stars sit there, unsparkling, a little softened, because the air above is layered and calm, and hardly mixing at all. The most beautiful sky and the most useful sky are not the same sky, and they never have been. Astronomers have a word for this, and it is a plain and rather lovely one. They call it the seeing. The seeing is good tonight, they say, or the seeing is poor, and they mean the steadiness of the air, and nothing about clouds or brightness or transparency at all. It is the single most important thing about an observatory, and no instrument can improve it, and no amount of money can buy it, and the largest telescope in the world on a night of bad seeing is worse than a small one on a good night. This was understood very early, and the man who understood it first, so far as I know, was Newton, who wrote about it in his book on light around 1704. He had noticed that the stars trembled and worked out that it was the air, and he wrote that the only remedy was to find the most serene and quiet air, such as might perhaps be found on the tops of the highest mountains, above the coarser clouds. That is exactly right, and it was 300 years ahead of anything anybody could do about it. It is why the great observatories are where they are. Not near universities and not near cities, but in a small number of very particular places on this planet where the air happens to arrive smooth. On top of Mauna Kea in Hawaii, 4,000 meters up, in the middle of an ocean, where the wind has crossed thousands of kilometers of flat water and arrives in even layers with nothing to stir it. On the ridges of the Atacama in Chile, the driest desert there is, where it has not properly rained in living memory. On a mountain in the Canary Islands, above a permanent sheet of cloud that acts as a lid on all the turbulence below it. The astronomers go up there and sleep during the day and work in the cold, and what they have gone up for is to get above as much of that trembling as they can. Even at those places, the very best nights give an image blurred to about 1/3 of a second of arc, which is to say that a telescope of any size at all, on the finest mountain on Earth, sees no more detail than a rather modest instrument would if the air were not there. That is what finally drove people to put a telescope outside the atmosphere altogether. Not to get closer to anything. Space is not closer to the stars in any way that matters. It was to get away from the last 100 kilometers of restless air, the thin, untidy layer we have been discussing all evening, the same one that makes the day blue and the evening red and holds the clouds up. Everything difficult about looking at the sky is caused by the thing you are breathing. But before we leave the trembling, let me tell you what was eventually done about it from the ground, because it is one of the cleverest things people have made, and it is only about 30 years old. If the air is a set of shifting lenses that distort the light, then in principle you could put another lens in the path, of exactly the opposite shape, and cancel the distortion. The difficulty is that the air changes its shape 1,000 times a second, and so your corrective lens would have to change its shape 1,000 times a second as well, and it would have to know what shape to take. Both of those turn out to be possible. The mirror is made thin and flexible, and behind it sit hundreds or thousands of small pistons that can push and pull its surface by amounts smaller than a wavelength of light. And it is bent into a new shape hundreds of times every second, all night, quietly, while the observation is being made. And to know what shape to bend into, the telescope watches a star. Any bright star near the thing being studied will do, because it is a point, and any distortion in it is entirely the atmosphere's doing. Measure the mess in the star, apply the opposite mess to the mirror, and both the star and everything near it come into focus. And when there is no convenient bright star in that part of the sky, which is most of the time, they make one. They fire a laser up into the sky, tuned to a color that a thin layer of sodium atoms about 90 kilometers up will absorb and give back. That layer, which is largely the residue of meteors that burned up over millions of years, glows faintly where the beam strikes it, and produces an artificial star exactly where it is wanted. So the observatory sends up a thin beam into the dark, lights a spot in the debris of ancient meteors, watches how the air is disturbing it, and bends a mirror to undo the disturbance, 1,000 times a second, for as long as the night lasts. And the images that come back are as sharp as they would be from space. I like that this was the eventual answer. Not to remove the trembling, which is impossible, and not to go somewhere without it, which is expensive, but to measure it honestly, several hundred times a second, and lean the other way by exactly as much. So here is the arrangement of the sky above your roof tonight, in full. The stars are steady, genuinely, physically steady, in the only sense that matters to a person lying in bed. They are all moving, in fact, traveling through the galaxy at tens of kilometers every second, in their own directions, on their own long paths, and the patterns we see are pure accident. But they are so far away that it takes 1,000 human lifetimes for any of them to shift a distance you could cover with a fingertip. Nothing you can see up there will look different tomorrow, or next year, or in the year that your great-grandchildren are old. Every civilization there has ever been has looked at essentially one sky. The painters in the caves in France 17,000 years ago looked up at night and saw very nearly what you will see from your window tonight. The Egyptians, the Babylonians, the sailors of every ocean, everyone who ever navigated by a star or was frightened by a comet, all of them were working from the same arrangement you can walk outside and check. It is one of the very few things that has been genuinely shared by everybody who has ever lived. The trembling, meanwhile, is entirely local. It is a few kilometers of air, warmed unevenly by ground that was in the sun this afternoon, folding over on itself in the dark, throwing thin patterns of light across your garden at the speed of the high wind. 800 years of perfect silence, and then 30 millionths of a second of shivering, and then your eye. I think that is the right way round, and I think it is a good arrangement for a night. The old and enormous things are calm. The near and thin things are restless. The restlessness is genuinely there and genuinely small, and it does not reach any further up than the weather. And it will settle. Later tonight, in the small hours, when the ground has finished giving back the heat it took in during the day, the air over your house will grow more even than it has been since morning. The stars will steady. Anybody out at 4 in the morning will notice that they have stopped sparkling so hard and have become quiet and hard and clean. The sky calms down before you wake, and the light in your window tonight is old. Not metaphorically. The particular light entering your room from any bright star left that star before you were born, and in most cases, before anyone in your family was born. It has been traveling in a straight line ever since, through nothing, at the only speed it has, unable to stop or slow or wait, arriving tonight because it happened to leave then. It arrives on your bedroom floor whether or not you are awake, and whether or not the curtains are open, and it has made no arrangements and expects nothing. So if you look out once more before you sleep, and the low bright one is shivering, you may know exactly what you are seeing. A perfectly steady thing, 8 centuries away, arriving through a few kilometers of warm, restless air over your own roof, on the very last morning of a journey it began before your country had its name. Let it shiver. It is not the star that is unsteady, and it never was, and the part that is unsteady will have calmed by 4 o'clock. Next, the sounds of the night, and why a train 2 towns away can be in your garden at 2 in the morning. You may have noticed, if you have ever been awake at the wrong hour, that the world is not merely quieter at night. It is differently arranged. Things arrive that are not there in the daytime. A train you never hear at noon goes through some cutting several towns away, and you hear every carriage of it. A dog barks on a farm, and it might as well be in the lane. A road you did not know existed produces a car, once, at 2:30, and the sound of it comes up the valley and passes through your open window and goes away west, and you can follow the whole of it. The usual explanation is that it is quieter, and that you are simply able to hear what was always there. That is true, and it is the smaller half of it. There is a real physical reason why the night brings you sounds from farther away, and it has nothing to do with your ears or with the absence of traffic. The night does something to the air itself, and the air does something to the sound, and the effect is that a lid is placed over your part of the world for a few hours. I would like to explain the lid, but first, briefly, what sound actually is, because it is even more insubstantial than the clouds were. Sound is not a thing traveling. Nothing crosses the fields from the train to your window. No material arrives. What happens is that the train shoves the air next to it, and that air, compressed, shoves the air next to it, which shoves the air next to that. A little squeeze, passed along, molecule to molecule, out in all directions like the ring on a pond. Each molecule of air moves an extraordinarily small distance, and then goes back to more or less where it was. It is the squeeze that travels, and the squeeze is nothing at all. It is a pattern of slightly crowded and slightly thinned air, moving through a medium that stays behind. The same trick as the wave in the river and the cloud standing over the field. A shape moving through material that does not go anywhere, and the amounts involved are almost absurdly small. When you hear a quiet conversation in the next room, the air in your ear is being pushed back and forth by a distance smaller than the width of an atom, and your eardrum is following it faithfully. Your ear is sensitive to the point of impossibility. Made much more sensitive, it would begin to hear the air molecules themselves colliding with the eardrum, a constant hiss, and there would be no such thing as silence for you ever again. That is very nearly where the design stopped. Your hearing is about as good as it is physically worth being. The squeeze moves at about 340 meters every second, which is a useful number to carry because it means sound takes 3 seconds to cross a kilometer, and that is why you may count after the lightning and divide by 3 and know how far away the storm is in kilometers, and why the answer is nearly always further than you expected. Now, the important property, the one that makes this whole chapter. The speed of sound depends on the temperature of the air, not on the pressure, which surprises people, and not on how thin the air is. On the temperature, and only that. Sound is passed along by molecules bumping into one another, and in warm air the molecules are moving faster, so they get to their neighbors sooner, so the message travels more quickly. The rate is simple and dependable, about 0.6 of a meter per second faster for each degree warmer. So sound goes faster through warm air and slower through cold air. Hold on to that, because everything follows from it. Now think about a summer afternoon. The ground has been in the sun all day. It is hot, far hotter than the air, and it warms the air lying directly on it. So the air near the ground is warm, and the air above it is cooler, and the air above that is cooler still, all the way up, in the ordinary arrangement that holds nearly everywhere in daylight. A sound leaves a source, say a church bell in a village 2 kilometers off. It spreads out in all directions, including sideways toward you, close to the ground. But that sideways part of the wave has its lower edge in the warm air near the ground, and its upper edge in the cooler air a little higher. So the bottom of the wave is traveling slightly faster than the top of it. And when one edge of a wave outruns the other, the wave turns. It has to. It pivots, exactly as a column of marching men turns when the outer file walks faster than the inner one. The bottom is fast, so the wave tips upward. The whole of the sound bends up into the sky, and leaves the ground behind. That is what happens to sound on a hot afternoon. It goes away over your head. Within a few hundred meters of the source, the sound that was traveling toward you along the ground has been lifted clear of you entirely, and it goes on up, into the air, out toward the clouds, and is not heard by anyone. There is a name for the region you are standing in. It is called an acoustic shadow, and you are in one for most of every summer day of your life. The daytime leaks its sound into the sky. Everything you do not hear in the afternoon has not faded away and has not been drowned out by traffic. It has gone up. Now the sun goes down. The ground begins to lose its heat. It does this by radiating it away into the sky, straight up, into a night sky which is very cold. And on a clear night it loses heat fast, because there are no clouds to send any of it back. So the ground cools. And it cools the air lying on it, which is why the mist forms in the hollows first, and why the grass is wet at 4 in the morning when nothing rained. By the small hours the arrangement has turned upside down. The air near the ground is cold. The air above it is warmer. There is a layer, perhaps 100 meters thick, perhaps 300, of cool air lying under warmer air like water under oil. Meteorologists call it an inversion, which is a dull word for something that changes the whole character of the night. And now do the same thing with the bell. The sound spreads out, and the sideways part of it has its lower edge in cold, slow air near the ground, and its upper edge in warmer, faster air above. The top is fast now, so the wave tips the other way. It bends down. Everything that would have escaped into the sky is turned back toward the ground. The sound that left the bell at a slight upward angle, which in the afternoon would have been lost over your head, climbs a little, curves, and comes back down, and lands 2 or 3 kilometers away, in a garden, on a person standing at a window. And when it strikes the ground it bounces, and goes up again, and is bent down again, and lands again further on, and again. The sound goes bounding across the countryside in long, low arcs, under a lid it cannot get through, arriving at places that would never have received it in daylight. That is the lid. It is not a surface, and there is nothing there, exactly as there was nothing at the flat bottoms of the clouds. It is a change in temperature with height, and it acts on sound as a mirror acts on light, and it is over your house on most clear, calm nights of the year. The night does not merely fail to interfere, the night actively delivers. So the train at 2 in the morning is not louder, it is not closer, nobody is running it differently at that hour. What has changed is that the air has stopped throwing its sound away and started handing it back down to the ground, and your window is a place where some of it lands. You are receiving something that in the afternoon would have gone to the clouds. And this explains a small mystery that most people have half noticed and never resolved, which is that the distances involved are odd. Sound at night does not simply fade with distance in an orderly way, it arrives in patches, because those bounding arcs touch the ground at intervals. Between the places where the sound comes down, there are gaps, and in the gaps there is nothing. So on a still night there can be a village that hears the goods train clearly, and a farm halfway between that hears nothing at all, and the people in each place will disagree entirely about what happened at 2 o'clock, and both will be certain. Now let me add the wind, because the wind does the same thing by a different route, and it explains the rest of it. Wind is slower near the ground than it is higher up. It has to be. The ground drags on it, the trees and buildings and the roughness of everything slow it down, and so wind speed increases with height, always, everywhere, on every windy day there has ever been. And a sound traveling downwind gets a push from that wind, and gets a bigger push higher up where the wind is faster. So the top of the wave runs ahead, and the wave tips down, and the sound is bent toward the ground exactly as it is on a calm, cold night. And a sound traveling upwind meets the reverse. The top of the wave is held back more than the bottom, and the wave tips up, and the sound is lifted away over the listener's head. So sound goes downwind and refuses to go upwind, and it has nothing to do with the wind blowing the sound along, which is what everyone assumes and which cannot possibly be right, since the wind moves at perhaps 5 meters a second and the sound at 340. It is the same bending. The wind is only another way of making the upper air quicker than the lower. That is why you hear the church across the valley on some evenings and not on others, when nothing about the church has changed, and why a person shouting to you from upwind cannot be heard while you can be heard perfectly by them. There is one further thing the distance does to the sound, and it is why the night sounds have the particular quality they have. Air absorbs sound as it goes, and it absorbs the high notes much more eagerly than the low ones. The mechanism is that the molecules of air, chiefly the nitrogen and the oxygen, can be made to spin and vibrate by a passing sound wave, and they take a little energy from it when they do, and give it back as a trace of heat. Rapid vibrations are taken far more readily than slow ones, so over a kilometer or two, the top of the sound is quietly removed. That is why distant thunder rumbles and near thunder cracks. It is exactly the same noise. The crack of it, which is the high part, has been absorbed on the way, and what is left is the long, low, rolling remainder. It is why the train at 2 in the morning is not a clatter, but a low pulsing, and why a distant motorway is a hum without any edge to it, and why you can hear the bass through a wall from a party 3 houses down, and nothing else whatsoever. Low sounds survive distance. High sounds are for the neighborhood only. And here is a thing that has always pleased me. The animals that need to speak over a long way have all discovered this, without conferring. The lion roars low. The bittern booms in the reeds and can be heard 4 or 5 kilometers away across the marsh. The largest owls hoot far lower than the small ones. The fog signals on lighthouses are low, and always were, long before anyone worked out why they had to be. And the elephants speak in notes so low that people standing beside them thought for many years that they were silent, and a great deal of what an elephant says travels several kilometers through the bush, and further at night when the air has settled into its inversion, which is precisely when elephants do most of their long-distance talking. Everything that needs to be heard from far away has arrived at the same answer. At night the world is delivering you sounds from a long way off, and by the time they arrive, the air has taken the treble out of them. That is the whole recipe for the sound of the small hours. Distant, low, soft-edged, arriving in patches, and none of it coming any closer. Water does all of this more strongly than land does, and if you have ever been on a lake in the evening, you have heard the result. Water changes temperature slowly. It holds the heat of the day long after the land has given up. And so, on a summer evening, the surface of a lake is often warmer than the air above it, and there is a shallow layer of cool air sitting directly on the water under warmer air. A perfect inversion, a few meters thick, lying flat over a mirror. Sound travels across that as though along a pipe. Voices carry astonishingly far. People on the far shore of a lake at dusk can be heard word for word, and they have no idea, and they are usually saying something ordinary about dinner. Rowers have always known this. So have people who fish, who learn to be quiet on the water without ever quite knowing why the water is different. And there is a version of all this happening about 4 meters from you, in the room where you are lying, which I would like to come to now. Snow, first, because it is the clearest case. Everyone knows that a heavy snowfall makes the world silent, and it is usually put down to there being nobody about, and that is again the smaller half of it. Fresh snow genuinely absorbs sound, and it is very good at it. New fallen snow is mostly air. It is a loose pile of crystals with an enormous amount of open space between them, all of it connected, all of it open at the surface. And when a sound wave arrives at that surface, it goes down into the spaces rather than bouncing off, and it rattles about in there, and the friction of the air moving in those tiny passages takes the energy out of it, and it does not come back. It is precisely the same reason that the panels in a concert hall are porous, and the reason a room full of curtains is quiet. A field of fresh snow can absorb the majority of the sound that lands on it. So on the night of a snowfall, the ground has stopped reflecting. The air has been washed clean by the falling snow, and the flakes themselves are breaking up the sound as it passes. Everything is being taken in, and nothing is being handed back. That is a real physical silence, and it is one of the few genuine ones available on this planet. And it does not last. Once the snow settles and hardens, and especially once its surface melts a little and refreezes, it becomes smooth and dense and reflective, and then it does the opposite. An old crusted snowfield throws sound back beautifully, and a frozen lake even more so, and sound over hard snow at night carries as far as it does over water. So the first night of the snow is the quiet one, and the third night is the one on which you can hear a car 5 kilometers off. And in your room, the same rules are quietly at work. The reason a bedroom at night sounds the way it does is that most of the high frequencies have been taken out of it by soft things. The bedding, the curtains, the carpet, the clothes, all of it absorbing exactly as the snow does. That is why a bedroom sounds gentle and a bathroom does not, and it is why an empty house that has just been moved out of sounds so strange and hard that people remark on it. You have arranged, without thinking about it, a room that takes the edges off sounds. Everybody does. It is one of the very few things that every human culture has independently agreed upon. And in that soft room, at some point, when everything outside has gone quiet and the traffic has stopped and the house has cooled and stopped ticking, you may become aware of a faint sound with no source. That is you. Some of it is blood. The vessels near your ear carry a considerable flow, and in a quiet enough room, on a quiet enough night, you hear it as a soft rhythmic presence, and it is why an ear pressed against a pillow sometimes seems to have a C in it. And some of it is the hearing itself. The inner ear is not a passive instrument. It contains cells which actively amplify what arrives, straining forward, and they are so eager that in a very quiet place they can be heard working. Your ears make a faint sound of their own. In a proper anechoic chamber, where all outside sound is removed, most people report a high, thin ringing, and then, after a while, their own body, loudly. Perfect silence turns out to be unavailable, and unwelcome when it is offered. People do not last long in those chambers. What we want is not silence but softness, and a soft room with distant sounds arriving gently is very close to the ideal condition for a human being to lose consciousness in, which is presumably why it is the condition we have all been arranging for ourselves for as long as there have been rooms. So that is the night, then, in sound. The ground has given its heat back to the sky, and the cold air is lying in the low places, and above it the air is warmer, and the whole arrangement has become a great soft ceiling that bends sound down instead of letting it escape. The train 2 towns over is being handed to you by a lid you cannot see. The high notes have been taken out of it on the way, so it arrives low and round and without any hard edges. It touches down here and not there, in patches, which is why your neighbor will say they heard nothing. And none of it is coming closer. That is the thing I would leave you with from this chapter. Every sound arriving at your window tonight is a sound leaving somewhere else. The train is going away. The car in the lane has already passed. The dog has finished. Each one of them reaches you at the end of its own small journey, spread thin over the distance, robbed of everything sharp, arriving at your ear as the last soft remainder of an event that was over before you heard it. There is nothing in the night sounds that is approaching. Let them land. They have been bent down out of the sky especially, and they have come a long way to be that quiet. Earlier tonight I told you that there is no blue above your roof. I should now tell you that there is a genuine blue on this planet, and that it is lying in the ocean basins, and that it got there by a completely different route. Almost everyone assumes the sea is blue because it reflects the sky. It is a reasonable guess. It is what I would have said as a boy, and it is largely wrong. The sea does reflect the sky, certainly. Look at a lake from a distance at a low angle, and you are seeing a sheet of metal with the weather lying on it. But lean over the side of a boat and look straight down, where you are seeing into the water rather than off it, and the blue is still there. Do it under a gray overcast, with no blue anywhere in the sky to borrow from, and the blue is still there. The water itself is blue. genuinely, intrinsically blue, in a way the air genuinely is not. And the mechanism is the opposite of everything I described in the first chapter, which is why I have saved it for now. Up in the air, nothing is absorbed. The molecules take no light for themselves. They catch the short waves and fling them sideways, and the color you see is entirely a matter of direction, and the blue arriving at your eye never came from the direction you are looking. In water, nothing is flung sideways in the first instance. The water takes light in and keeps it, and it keeps the colors unequally. Here is how. A water molecule is bent, always at the same angle, two hydrogens on an oxygen, and it can be made to flex. It stretches and bends on its hinges, and it does this at certain particular rates and not at others, the way a bell will ring at its own note and no other. And it happens, by an accident of chemistry that nobody arranged, that the energy carried by red light sits very close to what those vibrations want. So when red light passes through water, the molecules take it. They absorb it, they flex, and the light becomes a trace of warmth and is simply gone. Orange goes nearly as easily, yellow after that. Green is much more reluctant, and blue is the most reluctant of all, and passes through water more or less unharmed for a very long way. So the color of the sea is a subtraction, exactly as sunset is, but it is a slow one. It needs depth before it shows. In a drinking glass, water looks colorless, and that is why nobody suspects anything. The light has not traveled far enough for the subtraction to add up. A meter of it is still essentially clear. 2 meters, 3 meters, and you begin to notice something in a white-tiled swimming pool, a faint green cast in the deep end that is not in the shallow end. But go down through the open ocean, and the arithmetic becomes severe. At 5 meters, most of the red is gone. At 10 to 15 meters, all of it, which produces one of the strangest experiences available to a person on this planet, and divers know it well and are always surprised by it the first time. At that depth, a red thing is not red. It is brown, or gray, or black. Blood is green. A red diving glove looks like a lump of charcoal. Nothing has changed about the glove. There is simply no red light left down there for it to reflect, and a thing can only give back what arrives. Bring a lamp and shine it on the glove, and the glove is red again instantly, because you have brought the missing part of the spectrum down with you in your hand. Below 30 meters, the orange has gone the same way, then the yellow. Everything is now blue and green and a range of grays, and it is a world with a great deal of detail in it and almost no color, and photographs taken there without lights all look as though they were printed wrong. Deeper, the green goes too, and the whole world narrows toward blue alone, and then toward a very dark blue. By 200 meters, you are in what the oceanographers call the twilight zone, and it is well named. There is light, but there is not enough of it for a plant to live on. Photosynthesis has stopped. Everything below this line is living on food that falls from above, and has been for as long as there has been an ocean. And at about 1,000 meters, the last of it goes. Not dim, not faint, none. Below 1,000 meters, there is no daylight anywhere in any ocean on this planet, and there never has been. I want to give that its proper size, because it is easy to hear as a piece of trivia, and it is not one. The average depth of the ocean is about 3,800 meters. Not the deepest part, the average, the ordinary, unremarkable, middle-of-nowhere depth of the sea, which means that the overwhelming majority of the water on this planet, something like 9/10 of it, has been in permanent, absolute darkness since it arrived here. Not night. Night is a temporary condition that ends. This is a darkness with no counterpart, no dawn, no season, no variation of any kind, going back 4 billion years, and it is the largest habitat there is. By volume, most of the living space on this world is down there in the dark, and most of the animals on Earth live in it, and almost none of them have ever been seen by anybody. I find I have to sit with that for a while whenever I come back to it. We think of this as a bright planet because we live on the thin sunlit rind of it. The great bulk of the place is cold, black, still water, and always has been, and the blue we admire from the deck of a ship is only the top few tens of meters of it catching light before the light runs out. So when you look at a deep blue sea on a bright day, here is exactly what you are seeing. Sunlight goes down into the water. As it goes, the reds and oranges and yellows are taken out of it and turned into a trace of warmth. What is left, the blue, continues down, and some of it is scattered back upward by the water molecules themselves and by the fine particles suspended in it, and it climbs back out through the surface and reaches your eye. The blue of the sea is what water refuses to absorb, returning, and that is why the color deepens as you go further from shore. Coastal water is full of sediment and life and river silt, all of which scatter everything and muddy the effect, so it goes green or brown or gray. The open ocean far out is nearly sterile by comparison, very clear, very deep, and it goes an extraordinary dark blue that people who have crossed oceans always try to describe and never quite manage. Sailors call it blue water. It is one of the few pieces of nautical vocabulary that is precisely accurate. The same thing happens in ice, which is only water that has stopped moving, and it is easier to see because you can hold it. An ordinary ice cube is white or clear. It is small, and it is full of trapped bubbles, and the light has no distance to travel inside it. But go to a glacier. There, snow has fallen for centuries and been buried and pressed by the weight of the snow above it, until every bubble has been squeezed out and the ice has become dense and clear and old. Split it open, or look into a crevasse, or go into one of the caves that meltwater carves underneath. The inside is blue, not a pale hint of blue, a deep and improbable blue, the blue of an old medicine bottle, and it does not look like a reflection. It looks as though it is coming from inside the ice. It is. That is exactly what is happening. The light goes in, travels a long way through clear, dense ice, loses its red and orange and yellow to the same molecular vibrations, and what comes back out at you is what survived. You can see the same thing in a wave. On a bright day, at the moment a wave curls over and holds up a thin wall of ocean between you and the sun, that wall is green or blue, and for half a second you are looking through a meter or two of sea and seeing exactly which colors made it through. And in an iceberg, which is the most spectacular version, the white parts are the parts full of air. The blue parts are the parts that were compressed under 1,000 meters of glacier for 10,000 years before it reached the sea. An iceberg with a deep blue stripe through it is showing you a layer of ice that was once buried very deep and squeezed very hard. So there are two blues on this planet, and they have nothing to do with each other. The sky is blue because air scatters short waves sideways and lets long waves pass through. Nothing is absorbed, nothing is consumed. The color is a matter of direction. The sea is blue because water absorbs long waves and lets short waves through. Nothing is thrown aside. The color is a matter of depth, and what you see is the remainder of something that was eaten away. One is a scattering, one is a subtraction. They arrive at nearly the same color from opposite directions, and they have been lying against one another, sky above and water below, meeting in a line at the horizon for 4 billion years, in complete indifference to the fact that they match. Nobody arranged that either. Now let me take you down into the dark part, slowly, because there is something down there that I think is the gentlest fact in the whole of natural history. The light from the sun runs out at 1,000 meters. But the dark is not empty of light. The animals make their own. It is called bioluminescence, and it is not a rarity or a curiosity. In the deep ocean it is the normal condition. The best estimates are that somewhere between 3/4 and 9/10 of all the animals living below a few hundred meters can produce their own light. Think about what that means for a moment. The largest habitat on this planet is a place where nearly everything glows. The chemistry is simple enough, and it has been invented independently something like 40 or 50 separate times by unrelated creatures, which tells you how useful it is. A molecule and an enzyme meet in the presence of oxygen, and the reaction gives off a photon, and it gives off almost no heat at all. It is a far more efficient light than anything in your house. Nearly all the energy comes out as light rather than warmth, which is why they call it cold light. and it is almost always blue. Blue-green to be exact, right around the color that travels furthest through seawater. Every creature down there that makes light has, without conferring, arrived at the one color that carries. That is the same arithmetic I gave you a moment ago, running the other way. Water absorbs red, so a red lamp in the deep would be useless past a meter or two. Blue survives. So blue is what evolved, 40 separate times, in animals with no common ancestor that glowed. The physics of water chose the color of nearly all the light in the ocean, and the animals simply agreed. And there are exceptions, and the exceptions are the best part. There is a fish, a stout, ugly thing with a bad name, the loose-jawed dragonfish, which produces red light. It has a lamp under its eye that shines a deep red beam. Now, red light does not travel far in water, so as a headlamp it is nearly useless. But that is the point. Nothing else down there can see red. Every other creature in that darkness has eyes tuned to blue, because blue is all there has ever been to see. So the dragonfish carries a searchlight that illuminates its prey and is completely invisible to the prey it is illuminating. It hunts with a private wavelength. Nobody in that ocean can see what it is looking at. And there is the other side of the same trick. Since almost all light down there is blue, and since a great many animals hunt by looking upward for a silhouette against the last faint glow from the surface, an entire industry of counter-illumination has arisen. There are squid and fish that carry rows of small lights along their bellies, and they adjust them continuously to match exactly the brightness of the water above them. Seen from below, they disappear. They erase their own shadow. Some of them can even match the color as the water changes through dusk, and dim their lamps as the surface light dims, all night, without ever getting it wrong, because getting it wrong once is fatal. And there is the alarm. A great many small creatures, when they are seized, respond by lighting up brilliantly and refusing to stop. It seems a foolish thing to do while being eaten. It is not. The light attracts something larger, which comes to investigate, and which may well eat the thing that is eating you. It is a burglar alarm, and it works, and creatures that flash when attacked survive attacks more often than ones that do not. I want to come back to the surface now, because there is a last thing about deep water that belongs at the end of a chapter rather than in the middle of it. Down there it is cold, and it is still, and it is old. The water in the deep ocean is not the water at the top. It is a separate system, and it moves on its own schedule, and that schedule is very slow. Cold, salty water sinks. It happens in a few particular places, chiefly in the North Atlantic near Greenland and around the edges of Antarctica, where surface water is chilled hard by the polar air and made saltier by ice forming in it, and it becomes dense enough to go down. It sinks to the bottom and spreads out, and it begins a very long journey along the floor of the world. That water travels. It goes south along the bottom of the Atlantic, around Antarctica, up into the Indian Ocean and the Pacific, and eventually, somewhere, after a very long time, it works its way back up to the surface and is warm again and is rained on and is part of the weather. The whole circuit takes about 1,000 years. Which means that if you could sample the water at the bottom of the middle of the Pacific tonight and ask it when it last saw the sky, the answer would be somewhere around the year 1000. It went down off Greenland while people were still building the first cathedrals, and it has been in the dark, at 2 degrees above freezing, moving at the pace of a slow walk ever since. And it will surface eventually, and nobody will be there to notice. There is water down there tonight that has not been rained on since before your language existed. So that is the ocean then, from the top down. The first meter is clear and looks like nothing. By 5 meters the red has been taken out of the light and turned into a trace of warmth. By 15 there is no red at all, and blood is green, and everything red has become a dark shape. By 30 the orange has gone. By 200 plants can no longer make a living. By 1,000 the sun has ended entirely, and everything below is dark permanently and always was. That is 9/10 of the water on this planet, and most of the living room there is, and it is full of animals, nearly all of which glow faintly blue, Because blue is the only color that ever travels far in water, and they all worked it out separately. Half a kilometer of small fish rises toward the surface every evening and sinks again before dawn, everywhere, twice a day, unwatched. And along the very bottom, a slow cold current is carrying water that last touched the air 1,000 years ago. None of it is lit, none of it is loud, none of it requires anything of anybody. And the blue you see from a ship, that particular deep blue that people try to describe and cannot, is only what the water declined to absorb, coming back up out of a place that is mostly darkness, to the top few meters where the light still is. Next, the rain, and why nearly every drop that has ever fallen on your roof was snow 20 minutes earlier. Here is a thing that ought to be simple and is not. We have established that the sky is full of water. A single ordinary cloud holds 500 tons of it, divided into droplets so small that they fall at the speed of dust in a sunbeam, and there are 100 million of them in every cubic meter. So you would think that rain would be the easy part. The water is already up there. It is already liquid. It is already falling, slowly. All that is required is for it to fall a little faster. And yet clouds are remarkably bad at raining. You have watched this happen. A sky goes gray in the morning and stays gray all day, low and heavy and full, looking every minute as though it is about to open, and it produces nothing whatever, and you bring the washing in at 6 o'clock and it is dry. That cloud was not empty. It was carrying its full weight of water the entire time, and it simply could not get any of it down to you. The reason is a matter of size, and the numbers are severe. A cloud droplet is about 20 thousandths of a millimeter across. A raindrop, an ordinary one, the kind that makes a mark on a paving stone, is about 2 millimeters. That is 100 times wider. But things do not grow by width, they grow by volume. And 100 times wider means 1,000,000 times the volume. So to make one single raindrop, one of the many thousands that fall on your roof in an ordinary shower, you must gather together about 1,000,000 cloud droplets and merge them into one. 1,000,000. Each one of them drifting 2 millimeters from its nearest neighbor, falling at a centimeter a second, moving in a slow updraft, and they must find each other and join, one at a time, 1,000,000 times over, before anything at all can fall out of that sky. And they are extraordinarily bad at finding each other. That is the part that surprised me most when I first properly followed it through, and it is worth explaining because the reason is rather beautiful. Two droplets in a cloud are falling. The larger one falls slightly faster because it is larger, and so it gradually catches up with the smaller one below it. Good. They will collide and merge, and we will be a step closer to a raindrop. Except that a falling droplet pushes a little flow of air ahead of itself. It has to. The air cannot be occupied by two things at once, so as the droplet descends, the air in front of it moves out of the way, curving around the sides. And the smaller droplet, being very small and very light and very responsive to air, gets caught in that flow and carried around the side of the larger one. It goes past. They never touch. They pass each other the way two polite people pass in a narrow corridor, each stepping aside, neither making contact. For droplets of nearly equal size, this happens almost every time. The collision efficiency, as it is called, is close to nothing. They can approach each other 1,000 times and merge on none of them. So the whole scheme is stuck at the start. The droplets are all roughly the same size, because they all condensed at the same height under the same conditions, and roughly equal droplets cannot catch each other. Something has to break the deadlock. Something has to make one droplet meaningfully bigger than its neighbors, so that it can fall fast enough to plow through the flow rather than be gently avoided by it. And once you have one large droplet, everything changes. Now it is falling at a real speed. Now it is sweeping through a great volume of cloud every second. Now the small droplets in its path cannot get out of the way in time. It collects them and grows and falls faster and sweeps a wider path and grows again. That is called coalescence, and it runs away with itself beautifully once it starts. The problem is always the starting. In the warm parts of the world, over the tropics and over warm oceans, it does start, and it starts through sheer patience. Those clouds are very deep and very wet, and the updrafts in them are strong, and a droplet can be carried up and down inside one for a very long time. There is turbulence, which flings droplets together at angles that occasionally defeat the polite corridor problem. And the droplets are not perfectly equal, because the specks they condensed on were not equal. A droplet that formed on a large grain of sea salt starts out fractionally bigger than one that formed on a mote of dust. That fractional head start is enough, given ours. So tropical rain is the product of a million lucky collisions, arranged by a cloud that had the depth and the time to keep trying. It is called the warm rain process, and it is why rain over the tropics tends to arrive in enormous, soft, heavy drops, and why a downpour in Java or Brazil feels physically different from a shower in Europe. But over the parts of the world where most people live, in the temperate latitudes, this hardly ever works. The clouds are not deep enough and not warm enough, and the droplets do not get long enough. And yet it rains constantly in those places. It rains on Sweden and Scotland and Oregon and northern Japan more or less permanently, out of clouds that by rights ought not to be able to manage it. So there is a second mechanism, and it is a cold one, and it is the reason for this chapter. Go up. 2 or 3 kilometers above your roof, on very nearly any day of the year, anywhere in the temperate world, the air is below freezing. The upper part of every substantial cloud is colder than ice. In January, obviously, but also in July, over a hot afternoon, above a field where people are lying in the sun. Climb 3 kilometers and it is winter up there. And it is winter up there every day of every year. Now, you would expect the water in that part of the cloud to be ice. It is below freezing after all. It is not, or a great deal of it is not. Water is peculiar about freezing, in the same way it was peculiar about condensing. It does not like to begin. A droplet of pure water, suspended in air with nothing in it to start from, can be cooled well below zero and simply stay liquid. Not for a moment, indefinitely. It sits there at -10, -20, -30, perfectly liquid, in a state that physics calls supercooled, waiting. The reason is that freezing has to start somewhere. A few molecules have to happen to arrange themselves into the beginning of a crystal, and that first tiny crystal is so small and so sharply curved that it tends to fall apart again immediately. So the water waits for an excuse. Only at about -40 degrees does it finally give up and freeze on its own, without any help. That temperature is a genuine limit. Below -40 there is no liquid water in the atmosphere anywhere on this planet. But above it, in the great middle band between 0 and -40, the cloud is full of liquid water that has no business being liquid. You have seen the consequence of this if you have ever been somewhere cold enough. Freezing rain, which falls as ordinary liquid drops, supercooled all the way down, and then turns to ice the instant it touches a branch or a road or a wire, because the touch is the excuse it was waiting for. A whole forest can be glazed in an hour that way. It is beautiful, and it brings down power lines. And the same thing coats an aircraft wing, which is why aircraft carry heaters on their leading edges. So in the top of a summer cloud, over your house, over a hot afternoon, there is a great mass of liquid water at 15 or 20 below zero, going about its business, waiting for something to happen. And here and there, something does. There are particles in the air that ice will start on, fewer than the ones water will condense on, and much fussier, but they exist. Clay minerals from deserts are good at it, volcanic ash, and remarkably, certain bacteria which are lifted off leaves and carried up into clouds in vast numbers, and which have a protein on their surface that ice finds an ideal template. Some of the ice in the sky above you tonight began on a living thing that was on a leaf last week. So on one of these, an ice crystal forms. One among perhaps a million liquid droplets, all of them supercooled, all of them at the same temperature. And at that moment, something quietly decisive happens, and it is one of the loveliest pieces of physics I know, because it is entirely a matter of bookkeeping. Water molecules are held slightly more firmly in ice than they are in liquid water. Ice is more comfortable, if you like, which means that at any given temperature below freezing, fewer molecules escape from ice into the air than escape from liquid water. And that means the air around them cannot be in balance with both at once. If the air is exactly saturated with respect to the liquid droplets, holding as much vapor as it can without gaining or losing, then that same air is more than saturated with respect to the ice crystal. There is too much vapor for the ice, so vapor condenses onto the crystal. And now the air is very slightly short of vapor with respect to the droplets. So the droplets evaporate a little to make up the shortfall, and that vapor goes onto the crystal, and round it goes, continuously in one direction only, with no possibility of reversal. Every liquid droplet in the neighborhood is slowly disassembling itself into the air, and every molecule that leaves is finding its way to the ice. The crystal grows at the expense of everything around it. I want to say clearly how decisive this is, because it solves the whole problem in one stroke. The million collisions are not required. The crystal does not have to find anything or catch anything or collide with anything. It simply stands there, and the surrounding water hands itself over, molecule by molecule, through the air, because the arithmetic of vapor pressure permits nothing else. And it does it fast. In a matter of minutes, not hours, one ice crystal can assemble what a million lucky collisions could not. It was worked out in the 1930s by a Swedish meteorologist named Bergeron, who had noticed something while walking in the hills in Norway. He was staying above a fog layer, and each morning he walked down through it, and he noticed that when the temperature was above freezing, the fog was thick right down to the ground, but when it was below freezing, the fog had a clear space beneath it, as though something had swept it away from underneath. It had. The ice crystals had formed and had eaten the fog and had fallen out of it. He built the whole theory from that observation, and a German named Findeisen worked out the details, and it has carried both their names ever since, and it is the reason for nearly all the rain that falls on the temperate world. So now, in the top of the cloud, there is a growing ice crystal, and it is becoming heavy, and it falls. And as it falls, it does not fall through emptiness. It falls through kilometers of cloud packed with supercooled droplets. And now the coalescence problem is solved too, because the crystal is large and moving, and the droplets cannot get out of its way. They freeze onto it on contact. That is called riming, and it is what makes the small white opaque pellets that sometimes come down in a shower and bounce off the pavement, which people call soft hail or graupel, and which is simply a snow crystal that has collected so many frozen droplets that its shape has been buried. Or the crystal meets other crystals and they tangle. Ice crystals are branched, and they catch on one another readily, particularly when the temperature is near zero and their surfaces are slightly sticky, and they clump into the large, soft flakes that come down slowly in a mild snowfall. A single crystal is a millimeter or two. A clump of them can be a few centimeters across, and there are records of aggregates far larger than that in the right conditions, great soft assemblies coming down like feathers. So the thing that leaves the bottom of a cloud is snow, always. Whether it is a crystal, or a clump of crystals, or a crystal buried in frozen droplets, it leaves as ice. And then it enters the warmer air below. There is a height, on any given day, where the air passes through 0 degrees. Above it, ice. Below it, water. It is called the melting level, and like the flat bottoms of the summer clouds, it is a real and calculable altitude that nothing marks. On a warm summer day, it might be 3 or 4 kilometers up. On a cold winter day, it might be 100 meters above your garden. And on some days, it is at the ground, and on those days, the snow reaches you. Below that level, the flake begins to melt, and it does not take long. A snowflake falling through warm air melts in a few hundred meters, sometimes less. The delicate arms go first, then the structure collapses inward, and by the time it has fallen a kilometer below the melting level, it is a perfectly ordinary drop of water with no memory of anything. And then it lands on your window. So the summer rain running down the glass on a warm evening, The rain that people describe as warm rain, the rain you walked through in a shirt, was snow. 20 minutes earlier, 2 kilometers up, in air well below freezing, above a country that was in the middle of a heat wave. Nearly all of it. Every soft rain of your childhood, every downpour you ran home through, every drop that has ever struck the roof above the bed you are lying in this part of the world, began as an ice crystal on a speck of clay or a bacterium, grew by eating the water around it, fell as snow, and melted on the way down without mentioning it to anybody. There is one more thing about the melting level, and it is a small piece of magic that pilots and radar operators see every day. On a weather radar, in steady rain, there is a bright ring, a distinct band of strong reflection at one particular altitude, showing up far brighter than the rain above it or the rain below it. It is called the bright band, and it is the melting level made visible. The reason is that a snowflake, as it begins to melt, gets a film of water on the outside, while the ice structure is still large and open inside it. And water reflects radar far better than ice does. So, for a few hundred meters of its fall, each flake is a large object with a wet skin, which is the most reflective thing it will ever be. Above that band, dry ice. Below it, small compact drops. In between, briefly, wet snow. Every time you have seen rain on a weather map, that ring was in the data. And there is a version of it you can see with your own eyes in the mountains. On a day when the melting level sits partway up a hillside, you can stand at the bottom in rain and look up and see, at one particular height, a line across the slope above which everything is white and below which everything is wet. The line is sharp. It follows the contour of the hill exactly, all the way round, because it is not on the hill at all. It is an altitude. You are looking at the height at which the sky changes its mind. Now let me stay with the crystal, because I have told you what it does and not what it is. And what it is happens to be the most beautiful object this planet makes without any assistance whatever. Start with the molecule, because everything follows from it and nothing else is needed. A water molecule is bent. One oxygen, two hydrogens, and the two hydrogens do not sit opposite one another. They sit at an angle, and it is always the same angle, a little over 100 degrees, and no water molecule anywhere has ever had a different one. When water is liquid, the molecules cling to one another loosely and slide about and rearrange constantly, and the angle does not much matter. But when it gets cold enough that they stop sliding and lock into place, that angle decides everything. Because they can only lock together in the way the angle permits, and the arrangement that satisfies every molecule at once in 3 dimensions is a lattice with 6-sided symmetry. Not 5, not 8. 6, always, everywhere, in every snow crystal that has ever formed on this planet or on any other. That is not a preference or a tendency. It is arithmetic. The shape of the molecule forces it, and there is no alternative available. So every snowflake begins as a minute hexagonal plate, a 6-sided speck of ice, so small you could not see it, formed around its grain of clay or its bacterium. And then it grows, and this is where it becomes interesting. The crystal grows by taking water vapor out of the air around it. Now, look at the shape of that little hexagonal plate and think about which parts of it are best positioned to catch vapor. The corners. Obviously the corners. A corner sticks out further into the surrounding air than the flat faces do, and so it encounters more vapor, and so it grows faster. And having grown, it sticks out further still, and so it catches even more, and so it grows faster still. That is a process that feeds on itself, and once it starts, it cannot stop, and the result is that 6 arms come out of the 6 corners and begin to extend. And each of those arms is itself a small crystal with the same 6-sided lattice inside it. So the same thing happens on the arm. Small protrusions appear along its sides, at exactly 60 degrees to the arm, because 60 degrees is what the lattice permits, and those become side branches. And on the side branches, the same again. That is the whole architecture, a runaway process, repeated at every scale, constrained at every step by one angle inside one molecule. Nobody designs the shape. There is no plan for a particular snowflake and no mechanism that could hold one. There is only a lattice and a supply of vapor and an instability, running by itself in the cold. But here is the part that turns it from a piece of geometry into something closer to a document. What the crystal builds depends very sharply on the conditions it is in at that exact moment. Not roughly, sharply. At about -2 degrees, it makes flat plates, thin, simple, hexagonal, like small coins. Cool it a little to -5, and it stops making plates entirely and makes needles. Long, thin columns, quite unlike a plate, and if you saw the two side by side, you would not believe they were the same substance doing the same thing. Down at -10, it goes back to plates, and at about -15, in air that is very wet, it makes the elaborate branching stars that everyone thinks of when they think of a snowflake, the ones children cut out of folded paper, the ones on Christmas cards. Colder still, below -25, and it returns to simple plates and columns again, austere and geometric. So the temperature and the humidity, jointly, at every instant, dictate what the crystal is doing at that instant. It has no choice and no memory and no intention. It simply builds whatever the surrounding air permits it to build, right now. And then the conditions change, and it builds something different, and keeps everything it built before. Now put that together with what a falling crystal actually does. It does not fall in a straight line down through a uniform sky. It falls through a cloud, and a cloud is a turbulent place with updrafts and downdrafts and layers of different temperature and different moisture stacked through it and constantly shifting. So the crystal wanders. It is carried up and falls and is carried up again and drifts sideways and passes through a wet layer and then a dry one and then a colder one. It may take 10 or 20 minutes to come down, and in that time it visits a great many different sets of conditions, and it records every one of them in order in its own body as it goes. That is what a snowflake is. It is a written account of a journey through the air. The plate at the center is where it started. The needles halfway out are a layer at -5 that it passed through. The elaborate fern at the tip is a wet region at -15 near the end of the fall. You can read the whole route outward from the middle in the order it happened in the ice, which explains the two things everybody knows about snowflakes and nobody can explain. First, why are the 6 arms the same? Not because they were copied from each other. There is no communication between them, no template, no mechanism by which one arm could know what the others are doing. They are the same because they are on the same crystal, and the crystal is small, and so all 6 arms were in the same air, at the same temperature, at the same humidity, at every moment of the same journey. They wrote down the same story 6 times independently. That is all. 6 honest scribes recording identical weather. And second, why is no two alike? There is no rule requiring it. Nothing forbids 2 identical snowflakes. It is simply that the route determines the shape, and the routes are never the same. There are so many possible paths through a turbulent cloud, and the shape is so sensitive to each moment along the way that the odds of 2 crystals taking the same route are effectively nothing. Every snowflake is different because every journey is different, and for no other reason. There was a man who spent his life on this, and I would like to mention him because he was not a scientist by training, and he did something rather wonderful. His name was Wilson Bentley, and he was a farmer in Vermont, and he was 15 years old when he first looked at snow through a microscope his mother had given him. And he was so struck by it that he decided he wanted to keep the pictures, which in 1885 was not a simple thing to want. He spent 2 winters working out how to attach a camera to the microscope and how to catch a crystal on a cold blackboard and transfer it to a slide with a feather without breathing on it and destroying it, and how to work fast enough in an unheated shed that it did not evaporate before the exposure was done. He photographed his first snow crystal in January of 1885, and he was the first person who ever had. And then he kept doing it every winter for 46 years. He took over 5,000 photographs of individual snow crystals. He worked in a shed in the cold in Vermont with a camera and a feather, and he never made any money from it, and the neighbors thought he was a peculiar man. They called him Snowflake Bentley, which he did not mind at all. He is the reason we know what snowflakes look like. Every illustration of a snow crystal for the next 50 years came from his plates. And it was he who first said, from having looked at more of them than any person ever had, that no two were alike. He died of pneumonia in 1931, having walked home through a blizzard. Now let me correct one more picture in your head since we are here, because it is nearly universal and it is entirely wrong. The shape of a raindrop. Everybody draws it the same way, pointed at the top, round and fat at the bottom, a teardrop. It is on umbrella packaging and weather forecasts and children's drawings everywhere in the world. No raindrop has ever had that shape. Not one, ever, anywhere. A small raindrop up to about a millimeter is a sphere. Surface tension pulls it into the shape with the least surface area, which is a ball. And at that size, surface tension wins easily, and the drop is very nearly a perfect one. As it gets larger, the air pushing up against it as it falls begins to flatten the bottom. So a drop of 2 or 3 millimeters is not a sphere anymore. It is flattened underneath and rounded on top, and the correct comparison is a hamburger bun, or the top half of a loaf of bread. Larger still, 4 or 5 millimeters, and the air pushes so hard on the underside that it begins to hollow it out, and the drop becomes a shape rather like a parachute, with a bulging rim and a hollow center. And then it fails. At about 5 or 6 millimeters, the parachute breaks up, and the drop bursts into a number of smaller ones, which then fall and are stable, and that is the end of it. Which sets an absolute upper limit on the size of rain. There is no such thing as a raindrop larger than about 6 millimeters, anywhere, in any storm, because it cannot hold together. A cloud can throw down as much water as it likes, and it must do so in pieces no bigger than a pea. So the teardrop shape is not an approximation or a simplification. It is a shape that occurs when a drop hangs from something and is pulled off, from a tap or a leaf or an eye, and it lasts for an instant, and it has nothing at all to do with rain. And now the smell, because I would be sorry to leave it out. Everybody knows the smell of rain arriving on dry ground in summer. It is one of the most recognizable smells there is, and one of the most pleasant, and almost everyone finds it so. It has a name. 2 Australian scientists gave it one in 1964, having gone to the trouble of finding out what it was. They called it petrichor, from the Greek for stone and for the fluid that runs in the veins of the gods, which I have always thought was rather more poetry than a scientific paper usually permits. And it is not one smell, it is 3. The first is an oil. During dry weather, certain plants release oils that settle onto rocks and soil and accumulate there, and they seem to slow the germination of seeds, which in a drought is a sensible thing for a plant to arrange. When rain arrives, those oils are lifted off the ground and into the air. The second is a compound called geosmin, made by bacteria that live in soil, and this is the main one, and it is the earthy part. Your nose is extraordinarily sensitive to it. You can detect it at a few parts per trillion, which is better than a shark detects blood. Nobody is quite sure why we should be so finely tuned to the smell of wet soil, though one may guess that creatures who could smell water at a distance did rather well. It is also what makes beetroot taste of earth, and what occasionally spoils drinking water, and it is the same molecule in every case. And the third, on a stormy day, is ozone, made by lightning splitting oxygen molecules high up and carried down ahead of the storm by the downdraft. That is the sharp, clean note you smell before the rain arrives, rather than during it. When people say they can smell rain coming, they are right, and that is what they are smelling, and it has come down from a thunderstorm that is still some distance away. And the delivery mechanism is charming. 2 researchers filmed raindrops striking porous surfaces at very high speed, and found that a drop landing on soil traps a small bubble of air beneath itself. The bubble rises through the drop and bursts at the top, and flings a fine spray of tiny droplets upward into the air, each carrying whatever was on the ground. An aerosol, made by the rain, out of the ground, at the moment of contact. So the smell of rain is not the rain. The rain has no smell. It is the ground being thrown into the air a few thousand times a second by the impacts, and what you are breathing is the soil itself, in suspension, along with bacteria and oils and everything else that was lying there waiting through the dry spell. They found also that it works best on light rain. A downpour hits too hard, and the bubbles do not form properly, which is exactly right and matches what everyone knows. The smell is strongest at the beginning of a gentle shower on ground that has been dry for a while, and a violent thunderstorm on already wet ground gives you very little. So that is the rain then from the top down. It begins with a failure, a cloud full of water that cannot make a raindrop because its droplets are all the same size and politely step around one another in the air, and a million of them are needed for one drop. It is rescued by the cold. 2 or 3 kilometers up, where it is winter every day of the year, a mass of liquid water sits at 15 below zero, waiting for an excuse. On a grain of desert clay, or on a bacterium that was on a leaf last week, one crystal forms. And because ice holds its molecules a little more firmly than water does, every droplet in the neighborhood begins handing itself over through the air, molecule by molecule, in one direction only, until the crystal is heavy. It falls. It grows 6 arms because of an angle inside a molecule. It records the temperature and the wetness of every layer it passes through, in order in ice, and its 6 arms agree because they travel together. It collects frozen droplets and tangles with other crystals and becomes a flake. It leaves the cloud as snow, always, every time. And somewhere below, at the altitude where the sky changes its mind, it melts and finishes the journey as a perfectly ordinary drop of water, shaped like a small loaf of bread, and lands on your roof, and throws a little of your garden into the air, which you can smell through the window. There is rain falling somewhere within a few 100 kilometers of you tonight. There always is, and every drop of it was ice 20 minutes ago, and was vapor an hour before that, and was ocean at some point, and will be ocean again. Nothing in that entire sequence is being supervised. Not one step of it has ever been arranged or checked or maintained. It has been running for 4 billion years on nothing but the shape of a molecule, and the fact that cold air cannot hold what warm air can. And it will rain on this house again, and on every house, without anybody having to see to it. That was the 6 things. There is nothing after them. The sky above your roof is black now, and it is the same air that was blue this afternoon, holding still, with nothing to work on until morning. Somewhere within 100 kilometers of you, there are clouds in the dark, 500 tons each, every droplet falling, and none of them arriving. The stars are steady. They have been steady all evening. Only the last few kilometers of air were ever shivering, and by 4 o'clock that will have settled too. And the night has put its lid on, and is bending the faraway sounds gently down toward your window, with the sharp parts taken out of them. Under the sea it is dark, as it has been since the world began, and a layer of small fish 1/2 kilometer thick is rising toward the surface somewhere, as it does every evening. And 2 kilometers up, above some field or some town, it is quietly snowing into rain. None of it needs you. Not one of those things is being held up. Not one of them is being maintained. Nobody is watching the air to make sure it stays. The blue will be back over this house in a few hours, and it will not check whether anyone is awake to receive it. The clouds will have replaced every part of themselves 8 or 9 times before dawn, and will still be standing in the same shapes over the same fields. The light arriving at your window from the low bright star left before your grandmother was born, and it has not once slowed down, and it is arriving now, and it does not mind at all that the curtains are closed. Let it arrive. You have done enough today. Everything above your roof is doing the easiest available thing at every moment, and has been for 4 billion years. Falling slowly, rising slowly, bending gently downward, sinking into the dark and coming back up 1,000 years later, arriving after a very long time and asking for nothing. You may do the same now. Let the air be untidy. Let the water fall at the speed of dust in a sunbeam. Let the old light come in. Let the sounds land softly, all of them going away from you. The blue will handle the morning. Good night.